Okay. Now, I think we got the recording of this thing when it was on, when we took the strip off. If not, I'll do it again and put it in a video, but we're not going to take lab time to do it, okay? Now, I've got a magnet here. And you can see that this magnet is opposing this other magnet at a separation that's about equal to the length of a magnet. Now, if I release the thing, and I said we're going to measure ticks and we didn't. Well, if I release the thing, it starts rotating, okay? Not real fast. So now I'm going to do this with ticks. I'm going to release it on a tick, okay? And we're just going to see how long it takes to do a couple revolutions and how fast, how much it's slowing, okay? Ready? Tick, tock, tick, tock, tick, tock. I'm not synchronized. Going to do it again. Again, I have a problem with my neck, so I think if I come around to the other side, I can see it good. Okay, I'm going to do the same thing, but I'm going to release it from here, and you're not going to be able to see as well the separation. Had a domino handy. I can separate it by the length of the domino, but you see here now, so I've got tick, tick, tock, tick. I hit it with my finger when I released it. Try again. Tick, tock, 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 tick, tock. Okay, that's enough. You can infer if we've got good data, and I might have been blocking some of you, so you might not have seen what you needed to see, but hopefully everybody, or most everybody got it. It will have been slowing down. But from the previous data, we know about how fast it was slowing down. Okay. And I'm going to spin it again. We're not going to take data just while I'm talking, so that you can take data off the screen if you need to see how fast it's slowing down here. From that, you can infer how fast it was going when I released it. Because if we assume you have a linear velocity graph, which is pretty much true at this speed, you can figure out where that graph started because you get the average velocity. Now, the problem is you don't really get the final velocity, so you don't have really great data, but in principle, you could do that, especially if you let it go to rest, see how long it takes to go to rest. Now, my whole point is that this magnet and the other magnet had a potential energy by virtue of the position of this magnet in the vicinity of the other magnet, or I'll say these magnets here, okay? There is a potential energy. I can feel the force. You know, it's over a Newton of force right there. And if I try to get them really close, that force is really slippery. It's hard to do. You've done that with magnets, haven't you? Okay. But there's a potential energy there such that if I release one of the magnets, it'll gain a kinetic energy equal to the loss of that potential energy. And the potential energy is the amount of work it took to bring the magnets together against the magnetic force. Okay, I'll say it again. I have to do work to bring these magnets together. Okay, fortunately, I had a big breakfast and I have the energy to do that. Now, how much work did I do? Not much from here to here because you can't even really feel the force, but some, because the force out here is measurable. If I put the magnet that close, it really does have an effect. But starting in here, I start getting forces I can feel. And here, it's a pretty good force. And if I keep the thing from being slippery, I could push them all the way together. It doesn't take that much force. But closer I get them, the more work I did to bring them together, and the more energy I get when I release them. So we say we have a potential energy here, the potential to do work and increase kinetic energy. If I could lower the camera to where I could see the tabletop, I could, I'll actually do it anyway. So here they are, and there they go, right? Potential energy changed to kinetic. If that was too quick and you didn't get to see it, I don't want you to be deprived. There it goes again. Okay. Another thing, what happened to that potential energy? It became kinetic, but it was also losing energy to friction. Okay. Friction sucked energy away from it because friction was exerting a force to prevent it, to slow it down. Okay. A force in the direction opposite its motion. And that did negative work. Force in your direction motion does positive work. It tends to speed you up, right? Force in the opposite direction to your motion, if you're moving this way, is going to tend to slow you down. Okay. If you're trying to push your car forward, you push it from the back, and the force you exert is in your direction of motion. If you're trying to stop it, you get in front of it, which is not always a good idea. So don't practice that, but you would get in front of it. Make sure you don't trip and fall under it. And you exert a force and you can slow it down. Or you can get in the back and drag your heels, you know. Safest way is to open the door and, you know, be outside where thing won't run over your feet or anything. But again, in all those cases, you're exerting forces either to tend to speed the car up or slow it down. Okay. And it's worth storing that away and thinking about that, because when we formalize it with the mathematics, you'll understand what it's talking about. Instead of having a formula, it seems to have the right variables in it, so you use it whether it works or not, which is what people do a lot in physics class if you don't preach a lot. Okay, if I don't preach a lot. Okay. Another thing we can see here. Let's see, 1001, 1002, 1003, 1000. Yeah, that was rotating and still is pretty much at about a revolution every 6 seconds. Okay. So this magnet, which is about 50 centimeters from the axis, 50 centimeters, about 25 centimeters, about 20 centimeters from the axis of rotation, just ballpark. I think it's, 20.5 or something like that. But it's about 20 centimeters from the axis of rotation. What was its kinetic energy? How would you figure out its kinetic energy? Okay, to figure out the kinetic energy of this magnet, I've told you that this magnet is about 20 centimeters from the axis of rotation. Okay. And it was moving at about 1 revolution every 6 seconds. Might be a little faster than that this time. But, okay. But if it was moving at 1 revolution every 6 seconds, could you calculate its kinetic energy? Well, everybody knew in class 2 days ago the kinetic energy was 1/2 mv squared, so I assume everybody knows it now, even though nobody wanted to say it right away, okay? And I'm pretty sure I'm right about that. If I ask you to write down kinetic energy, you'd write down 1/2 mv squared. So we got to know what its V is. V is how fast it's moving. Okay, it's not a vector. It's not a vector V. Direction doesn't matter. V is how fast. Vector V is how fast and in what direction. Okay, and the direction keeps changing and is not relevant to that kinetic energy. Okay, well, the point is though, I ask, okay, so how are you going to figure out from that information how fast the thing is moving? And I wasn't getting any answers. And I said, okay, well, what's the path of this thing? Is it a rectangle? Is it an ellipse? Is it a hyperbola? Parabola? What's in average? Oh, it's a circle. Okay, well, so if this thing describes a circle and stays 20 centimeters from the center, how far does it go during a revolution? Nobody could, or at least nobody wanted to tell me. So, well, there's a formula, you know, there's something more important than the formula, but there's a formula. What's the formula? And finally, somebody, well, 2 pi r. Okay. So you could use that to figure how far it is. But I said, okay, but what's pi? Well, people wanted to give me a number, 3.1415926. And I don't know after that, I'm not even sure about that 6. It might be 5 or 7. But I think it's 6. You could plug the radius of that circle, which is 20 centimeters, into the formula and get an answer. But what is pi? Okay. Somebody finally told me, well, it's the diameter divided by the radius. That's what pi is. And an important distinction I want to make is between a formula and reality. Formula represents reality. Okay. And there's a simple series that, you know, if you did series in calculus 2, if you had calculus 2, some of you have only had calculus 1. There's a simple series that you can evaluate and evaluate pi to any number of decimal places, just a simple Taylor series. Okay. But fundamentally, the reality is any circle, if you divide its circumference by its diameter, you get pi. That's what pi is. It's not something that people just put in a formula that's about equal to 3.14. Okay? So think about that distinction between the reality and the formula. Once you know that pi is a ratio of circumference to diameter, it's how many diameters it takes to go around a circle, you can figure out everything else. If you know the calculus, you can figure that out. Okay? Start with that fundamental concept instead of a formula. And if you think of the formula first, remind yourself what pi means. Because you will naturally think of the formula if that formula is pretty well ingrained. All right. I'm not going to do ticks and talks because I'm going to ask you to observe this at home. Only going to take, 5 minutes to get the observations. I'm not going to start it real fast. About like this. That's about a 6-second revolution. Okay. And you don't have to take any data right now. I'm just going to let this thing come to rest. Okay. And while I do that, I'm going to write some things on the board and I'll probably talk about them a little bit as I'm writing them, but then I'll put the camera on it, do a quick summary, if I can find my chalk. I think the best $3 I've spent recently is getting these holders, so I'm not always losing my chalk. And then I put the white chalk in a red holder, so it really stands out. Because I'm always losing chalk in class. Trey will verify that. He's seen me spend hours hunting for a piece of chalk. He totaled it up over the whole semester. All right. So a couple of points in figuring out how fast a magnet is moving is you have to know that pi is the ratio of circumference to diameter. But first, you got to know that the thing's moving around a circle. Okay, so we have a beam here, top view, and we've got a magnet here. We got the center of the beam. And the beam is approximately 60 centimeters long, closer to 61. And the magnet is at some distance from the center, and this thing is rotating. And at 6 seconds per rotation, how fast is the magnet moving? I'm lapsing into cursive. I don't know how well y'all read cursive, especially the way I write it. So I try to keep it in print, but sometimes for speed, when you pretty much know. When I say how fast, you know we're talking about the magnet because of our context. Okay, well, first observation. The real question was, what's the kinetic energy of the magnet? I told you it was 50 grams. That should be pointing better at the magnet, but there it is. Okay. The kinetic energy, why would we want to know how fast the magnet is moving? Well, everybody knows that. Kinetic energy is 1/2 mv squared. And we know that m is 50 grams. So what don't we know? We don't know v. So we have to figure out how fast the magnet is moving. What information tells us how fast the magnet is moving? How long it takes to do a revolution? And how far it goes during a revolution. Okay. This isn't a formula. It's really how fast equals how far over how long. And how long could be a length. How long it takes to go how far. That's the idea. That's, you know, there's a formula for it. But if the idea is not intuitive to you, it needs to become intuitive. Okay. And I think be pretty clear on that. I'm just trying to emphasize how we need to go back to reality and our direct perception and what these things mean. Okay, how fast equals how far over how long it takes. How far? Well, I didn't give you how far, I didn't write it down, but it was 20 centimeters. So how far? I mean, I'd definitely write a circle, draw a circle, and indicate that the radius is 20 centimeters. So obviously diameter is 40 centimeters. Circumference, well, pi equals, by its definition, circumference over diameter. Okay, so how far is it moves distance equal to the circumference. So for your picture, you see this, there's a formula, 2 pi r for the circumference, or pi times d, but it comes from the definition of pi as circumference over diameter. So circumference is pi times the diameter. And in this case, that's then pi times 40 centimeters. Now, if you really know that and can think that through, then you're more secure if you say circumference is 2 pi r, because you can think, okay, well, that's pi times diameter, and diameter over circumference is pi, times circumference over diameter is pi, and all that stuff. Okay, that should all come out if you even think the formula 2 pi r. It should just be there like a flash of light. Okay, well, let me come back to the board because I've been writing, but we wanted to get that thing coming to rest. You know, if I pull it back a little bit, we'll go to the bottom of the board. Disadvantage is you get more of me. Okay, so if I was writing this out, I draw a little schematic, put in my information, indicate the thing's rotating somehow. Then the question, now I asked the kinetic energy of the magnet, so you probably want to write out K equals 1/2 mv squared. If you've got it on your paper, then you don't have to keep thinking about it. A lot of you were writing numbers and symbols, and maybe some right, some wrong, but you didn't have K equals 1/2 mv squared. So you did. You start with that, okay? That's okay to start with that formula, because right now we haven't derived that formula. Eventually I'll ask you to prove it, okay? Because remember, this is the energy it takes to get up to that speed, to get that mass up to that speed from rest. Okay, it's the work it takes to get to that speed. It's the, well, it follows immediately from some stuff you got last week and did pretty well on with the assignment. Okay, and seemed pretty well versed in class, but we want to get better. Okay, and one purpose of lab is to connect us to reality instead of a bunch of formulas. Okay, so now I also told you 6 seconds per rotation. And it would be good to have that written out one way or another. Okay. Didn't see anybody write out anything like how fast equals how far over how long it takes. And you could write that as a formula, V equals delta S over delta T. It's actually a V bar, okay? It's the average velocity. But we're assuming that the velocity stays pretty much constant for that one revolution. And from what we've already measured and what we've seen, we're pretty confident it doesn't slow down that much during a single revolution. At least not when it's moving reasonably fast. Okay, so we're going to use that. Knowing that it's slowing down, knowing the kinetic energy is actually decreasing a little bit, but we don't worry about that, but we can kind of keep that in mind. Okay, so how fast is how far over how long it takes? So how far? How are you going to calculate how far? You could write down circumference equals 2 pi r or pi d. But I think some people missed that. About half of you missed that. Half of you had this thing moving at 120 centimeters per second. Okay, which is unfortunate, 120 centimeters in 6 seconds. You got the 120 centimeters. I told you use 3 for pi just to do a ballpark calculation. So if you have 20 centimeters here, you have a 40 centimeter diameter, and your circumference, pi is your circumference over diameter, so the circumference equals pi times diameter, is pi times 40 centimeters. And if you use the approximation I made for pi, that's 120 centimeters. Now, if you use 120 centimeters per second, well, if that thing's going around in a second, I don't want you close to it because one of those magnets might fly off and hit you. Okay? I don't know if it would or not, but we could calculate the centripetal acceleration, which is v squared over r. V would be 120 centimeters. Square that, you get 1.44 meters squared, and divide that by the radius. Magnets at 30 centimeters, you get 1.44. You get about 1/2 g. Okay. Well, I don't think they fly off at 1/2 g. Now, I use something you don't know, that centripetal acceleration is v squared over r. If you know how to analyze an isosceles triangle, you can derive that. We'll see that later. Okay, my whole point here is nobody wrote it out that completely. But there are aspects of what I've written out here that you would have done well to write out instead of getting the wrong answer. Okay. Like I haven't completed it. It went 120 centimeters. Well, now we can feed that back into how far, okay? And how long is 6 seconds? And then out of that, we get centimeters per second. Also, 120 centimeters per second is this far, give or take a little. Thing really moved 1001 that fast? You can see it going around the circle. It wasn't moving this far in a second. Okay. So you also want to connect your calculations to the reality. Now, sometimes the calculations, you figuring out something about nanoparticles and, you know, oscillations of a cesium atom and stuff, and that gets pretty non-intuitive until you work with it for a while. But you can build intuition about that kind of stuff by making sure you think through the details of this calculation. Now, it's really a pretty simple calculation. And if you've done a few of them, then they become natural and you can start shortcutting it, but you want to be careful. It's real easy to overlook details, especially if you don't draw pictures and schematics. Okay. So take that as a lesson. So anyhow, it's 20 centimeters per second. We still don't have the kinetic energy. But now, if you want to do it with symbols, okay. But the feeling of the symbols is how far over how long it takes. And if you don't have the feeling of the symbols, you're not going to remember it as well, and you're not going to think of using it when you need to. Or you're going to be less likely to think of using it when you need to, okay? Think about what I'm saying. Okay, that's delta S over delta T equals 120 centimeters per 6 seconds equals 20 centimeters per second. Then assuming well, I messed up that's constant. Assuming constant V, I'll say constant speed because velocity is speed with direction. You'll still use V with the speed, but well, let's address other errors that I'm still seeing. That's 1/2 times 50 grams times 20 centimeters per second quantity squared, which equals 20 squared is 400. Too close to the edge of the screen, but I've got it in there. You can't see it, but I've written out the unit centimeter squared per second squared. And then you multiply all that out and you get 4,000 centimeters squared per second squared, which is 4,000 dynes. No, it isn't. It's 4,000 ergs. And it's not centimeters per second squared, it's grams centimeters per second squared. So now I am getting a little cramped. G for gram, centimeters squared per second squared. So if you look at the video, that'll be pretty safe. Okay. And that turns out to be 4,000 ergs, but then you can change gram to 0.001 kilogram and centimeters squared to 0.0001 meters squared or 0.01 meters quantity squared and find out that it's some fraction of a joule. Okay. And that would follow from what we talked about in class. And my arithmetic is wrong. Took half of 50 and got 10. That was kind of ignorant. It's 10,000 grams centimeters per second squared. Okay. Now I will ask you, when you write up what we did here today, to figure out the total kinetic energy of the magnets in that first observation. Okay. I'll put that in writing. And of course, now you could figure out the total kinetic energy of the magnets in this situation, where you again have about a 6 second, it's about a 5 second revolution, but from that, you should be able to tell me what the total kinetic energy of the magnets is. Okay. Then, did I tell you this? Because I think you were doing something. When this is worth doing. Needs to be done quickly. And easily. If I get the magnets apart. Without knocking the system over. Okay. So what I'm going to do is, you see this on video, or you can get yourself where you can see it where you're sitting. These magnets are one domino apart. And if I release them, some 1,002. Well, when I did it before, and the thing didn't try to fall over, and why did it fall over? Because I've got more torque on this end than on that end. I didn't have it balanced. Let's get it back in balance. Okay, when I did that before, took about 5.5 seconds to do half a revolution. So I'll put something about that on an assignment. All I'm going to ask you is, okay, how much kinetic energy did each magnet pick up? And then when we start measuring forces and stuff, which we might do a little of today, we can, are we recording? Yeah. When we start measuring forces, which we'll do a little of maybe, you can correlate the kinetic energy of all the magnets with the amount of energy you get from the magnet system. Okay? That makes sense? You're not going to account for all the energy because the beam has energy too, but we'll worry about that later. Okay. Now we've been going on for a good while now. And probably ought to take a 10-minute break. Then we'll come back for about 20 minutes and we'll be done. Okay.